Okay, so for this this video, we're taking a look at this topic, 5824. So in case you're watching this from home, this is where we are. So we're going to look at the wave speed equation. Tuning forks, 512 hertz. Tell that person that you're sitting next to how many cycles per second that is. You're on recording now. 512 hertz. How many cycles per second? 512. Thank you. So this tuning fork is vibrating, producing sound at a rate of 512 hertz. So I'm going to draw a little tuning fork here. And so tuning forks look like so. When they vibrate, they produce what kind of wave do you think? Longitudinal or transverse? It is longitudinal. So what it's doing is it's vibrating back and forth like so. And when it does that, it creates a series of compressions. And the air particles sort of get compressed in those areas. And then, of course, there's some areas that are sort of spread out. Now, you don't have to draw all this stuff. This just makes for a great video. So I'm going to put that would sort of represent what the waveform looks like. If I were to draw it as a transverse representation, it would look something like this. And so that sound is traveling at a certain speed. Now, I'd like to know that speed, so I'm going to put a little arrow on this to indicate the velocity. What is the speed at which that wave is traveling? If I know its wavelength, then I know that frequency. So I'm going to use the velocity is equal to frequency times wavelength equation that we looked at yesterday. The 512 cycles per second, 512 hertz, produces a wavelength. That distance there is 0.664 meters. And when you multiply those two together, I assume you have a calculator with you? Or you can do that math in your head, and if you do that math in your head, you get about 340. And then, of course, I would be interested in knowing what the units are. 340 what? Wait, that sounds like power. 340 hertz meters. Would you agree it's 340 hertz meters? Except the hertz is a per second idea. So when I say it's 512 cycles per second, that is often written as a seconds to the -1 power. So when I write that out, I say 340 meters per second. And so that would be the speed at which sound travels through air, at least room temperature air. Now, I don't want you to do a calculation here. Using this for number 2, I don't want you to do a calculation that's really complicated. Notice I'm going to use that speed, and I'm going to take a tuning fork that vibrates more slowly. So that tuning fork is now 256 hertz. So it's of slower frequency. What should happen to the wavelength if the speed is a constant?
Would the wave be like longer, I guess? Like bumps would be longer, longer.
So I thank you for trying that, right? Look at the 256. Would you agree that 256 is half of 512? So the frequency became half as great. So the wavelength would become twice as big. Now, you don't have to do a lot of fancy math. The idea behind that is that speed is a constant, 340 meters per second. That lower frequency is going to produce a longer wave. And that's simply because the frequency and the wavelengths are related to that wave speed. Now, if you want to do a calculation, you can. The wavelength would be the velocity divided by the frequency. I take the 340, I divide that by 256, and you get about 1.33 meters. And I trust that you can do that with your calculator. That 1.33 is twice as big as the 0.664. And that's because of that frequency velocity, or that frequency wavelength idea. So Shay, you are correct. Okay. One of the things that I'll have you guys do, probably on Friday, so I'm going to have you do a lab that involves this wave on a string thing. I want you to take a look at that picture for a second. What is the amplitude of that wave? What is its wavelength using the vertical ruler and the horizontal ruler? See if you can identify what is the amplitude, what is the wavelength. And then, if you feel confident with it, try letter C. What is that speed if the frequency is 2 cycles per second? Take a moment, see if you can answer those. Tell that person that you're sitting next to what you think those values are. What's the amplitude? What's the wavelength? And then try that speed. Okay, will you tell that person that you're sitting next to, not a lot of talking, you're supposed to talk more. What is the amplitude of that wave? What is the wavelength of that wave? Take a moment. Talk to them. Don't be shy. I'm glad I'm recording this because it's not picking up anything. Thank you for trying. I appreciate that. What did Captain say? You don't hold anything against them under you of them, right? You're a safety. Come on, you can do it. Ellie wasn't even here.
No.
It's new to her. How about Reagan? No? Connor Betts has it. No, I don't. Oh my God. CJ, way in the back. It gets better with distance, right? The further away that we are. You guys have that, don't you? All right, CJ, thank you. You're in a safe space here. You are being recorded. All right, CJ, what is the amplitude of that wave? It's okay if you make a mistake because we're going to correct you in a safe way. Go. Thank you. Yeah, it's the most common mistake that people will make is to take the full 1.6 and say that's the amplitude. Thank you for making that mistake. It is not 1.6. But I'm glad that you found it. I'm glad that you made that mistake because now others will not. And so, CJ, that's awesome. Thank you. How we define amplitude is a maximum displacement from, what's that position called? That is the equilibrium position of that string. So the amplitude is the maximum displacement from that equilibrium position. CJ, I think what you gave me was 1.6 being this entire thing, 1.6. But the amplitude would not be the entire 1.6. What would it be? Half of that. So it's the most common mistake. The amplitude would be 0.8 centimeters. Do you see where that comes from? Okay. Amplitude. You have to identify what that is from a drawing. Okay. Now, here I can take the amplitude, put it at about 0.8, just so you can see. And so here's a ruler I'll put up next to it. And so when I set this one into motion, you can see that wave. Now I can move this thing, and when you guys do this lab, you'll have a chance to be able to move some things around here. I'm going to pause it for a second. So I go to the very bottom there, and so this would be that. This is how I sort of created that, and you can see where that 1.6 comes from. It's actually a 0.8 meter amplitude. Okay. How about the wavelength? Thank you, Riley. Oh, say it one more time. 2 what? 2 meters. Okay. What do you now? When you look at this diagram, what are you looking at to determine that it's 2?
Where it starts to the bottom.
Okay, so where it starts is this one right here. Okay. Now, how far are you going over before you say the wavelength is completed? If I choose this one, I'd have to go over to the exact same point over here and that would be a full wavelength. It's got to be the exact same position doing the same thing. Now, this one is currently on its way down. Would you guys agree that's sort of on its way down at this point? It's on its way down. This one would also be sort of on its way down. Now, you might look at that and say, well, this is at the same spot, but if this one's going down, that one's going up. So the wavelength has to be from two successive points. Probably the easiest place to look would be at a crest or a crest. Those are easy to identify. Also, a trough to a trough. Do you see that from the trough to the trough? It might be easier to see that it's closer to about 3. Can you guys see it? Let's see, 2 to 5. Do you see I'm getting 2 to 5 is 3? Okay, amplitude we said was about 0.8. And the wavelength we said is about, Greek letter lambda, is about 3 centimeters. What do I do with these two numbers to determine the wave speed? What do I do with them? You would say nothing, because the wave speed does not depend on the amplitude. It depends on the wavelength and the frequency. So if I want to determine the wave speed, I use these two numbers. How fast does that thing propagate? You can do it. You don't need a calculator. Thank you. I'm going to write it down. It's 2 hertz. That's 3 centimeters. And that would become 6. And then it's not meters per second. It would be 6 centimeters per second. See how that works? Okay, those of you that were paying attention yesterday, which was everyone, you can answer this question based on Ian and Mai's demonstration at the end of the hour. If I take that cord and I make the tension tighter, so I tighten the tension, what will happen to the speed of that wave? Instead of 6 centimeters per second, will it go up, down, or stay the same? Turn it to the other person next to it. Come on. Turn it on. It will definitely increase. Thank you, Veronica. You are not alone on that. A lot of people are saying the speed will increase. And the reason that it does is because the speed will increase because, I'm going to say, the restoring force is bigger. F is bigger. Now, some of you were, I'm grading the speaker projects. I'm doing the seniors first, and I think I got every senior that turned it in. I got those grades back to you. That's because senior grades are due. There were some people that were struggling with why it is that the heavier weight paper actually performed better in many cases than the lighter weight. It seemed to be contrary to what you thought. But the heavier weight paper has a bigger restoring force. It's stiffer, maintains its shape better. And oftentimes, as long as I have enough force coming from the number of turns, I can get that to really vibrate quite well because that force is bigger holding those things together. What happened to the wavelength? It would, thank you. If I go to this, now if the speed, I'm going to write this down here, and I appreciate you trying this. If the velocity gets bigger and the frequency stays the same, shouldn't that make the wavelength bigger? If I'm increasing the velocity, then the wavelength will also increase. Okay. Questions for me before I stop this? I have a question for you. 8 minutes. Can you use that time to work on these four problems? 8 minutes. How long do you have per problem? 2 minutes. That's all you should need to be able to get through these things. I'm going to give you 8 minutes to work on this. During that time, I want you to work on these problems. If you don't finish it, it becomes that dreaded homework thing. But you should get it done in 8 minutes. Kevin's going to help me out. Right, Gavin? Will you help me out, Stephanie? Will you help me out? Thank you. On your side, each person gets one of these.